So it's been a while since we talked about uniform continuity. You all just already recalled to me the definitions. You all know what it is. Maybe I'll write down just what I was thinking. So we proved some things about uniformly continuous functions, and I'll make reference to several of the results in the proof of this last nice result about uniformly continuous functions. We proved that if you start with a bounded set and apply a uniformly continuous function to that bounded set, then the image is still bounded. So with a uniformly continuous function, you can't go from a bounded set to an unbounded set. If you like, I guess that's prohibiting anything that you might want to call a particle asymptote. If you, maybe more importantly, if you take a uniformly continuous function and a Cauchy sequence of things in the domain, then f sends that Cauchy sequence to another Cauchy sequence, even if the limit of that Cauchy sequence isn't in the domain anymore. So let's use some of those results, and let's prove, if you like, this was supposed to be advertised as the main good thing about uniformly continuous functions. If you take a domain U and a function, which is uniformly continuous on that set U, and a limit point of that domain U. Well, a limit point of U is the point where you can actually ask about the limit as x approaches p. Then the limit of this function as x approaches p exists. More readable? Okay. Let me also hit this button. Well, let's try to do it. So let's let U be a subset of R, and f from U to R be a uniformly continuous function, so p be a limit point of U. I need to show that the limit as x approaches p of f of x exists. Now, in terms of limits of functions, I don't have a good way to say that the limit exists without cooking up a guess for what the limit should be. But I do have such a thing called sequences. So let's try this. Let's take a sequence of inputs, a sequence of things in the domain, which converges to. Then, if the limit of this function exists, it should be the same as the limit of f of xn, where xn is that sequence I started with. So let's cook up that sequence. We'll show that the limit as n goes to infinity of f of x of n exists. And then, well, what do? I'll then, well, so if the limit as n goes to infinity of f of x of n, that exists, I can give it a name. I'll call that limit, I don't know, y is what I call it at then. Under those circumstances, if the limit as x goes to p of f of x exists, it only has one candidate. It has to be whatever that number is, that y is. So now that I have a candidate, I can try to prove that the limit as x goes to p of f of x is equal to y. And there could be one of two philosophies you could have. That's a thing about limits. So you might try to cook up an epsilon delta. That isn't what's in here. The other philosophy is we have this reformulation of all the stuff about analysis in terms of sequences. So instead, I'll use the sequential reformulation of the limit, and that's what I'll do here. Not because it's objectively easy, it's because I'm already using sequences. And it really fits into the theme of the other stuff of these notes, because everything is been in terms of sequences for the past couple of words. So let's try to do it. Let's try to follow that path. So this point P is another point of view. From that, I can deduce that there's a sequence of things in U, x sub n I'll call it, such that this sequence, x sub n, converges to P. And let's see, I'm going to make an appeal to theorem of 30.6 myself. Let's recall what that theorem says really quickly. So theorem 3.6.11. So if you have a uniformly continuous function, if f is uniformly continuous on U, then for every Cauchy sequence of elements of U, f of x sub n is also Cauchy. And so let's think about what I just said about the plan of attack. This x sub n converges to p. I would like to get f of x sub n to converge. Well, let's see what we can do with that. There's an equivalent notion to convergence that doesn't make reference to the limit anymore, right? F of x sub n converges, period, is the same thing as f of x sub n being Cauchy. So I would like f of x sub n to be Cauchy. But according to that theorem that's on the previous page, I'll be happy if I can get x sub n to be Cauchy. Is this sequence Cauchy? Yeah, why is this sequence Cauchy? Because it's convergent. Since this sequence x sub n converges to p, I guess I don't even care about this to p right now, this sequence is Cauchy by this theorem that's on the previous page and is hopefully actually 3.6.11. I get that f of x sub n is also Cauchy. Because this function is uniformly continuous. That's one of the assumptions. By the Cauchy convergence theorem, f of x sub n is then convergent. I have lots of trouble spelling convergent. Is it ENT or ANT? Convergent or convergent? That's good. Okay, so that's good. We have this limit of that sequence, y. Now, if the limit as x approaches p of f of x exists, it has to be the same as the limit of as n goes to infinity of f of x sub n, because that sequence converges to p. So the limit only has one candidate. It has to be y if it exists. It's either y or it doesn't exist. So if I'm going to show that this limit exists, I'd better actually show that the limit is equal to y. So that's what I'm going to try to show. And there are now two philosophies you can have. This is a statement about a limit, so there should be an epsilon delta proof. After we go through this, if people want to see the honest epsilon delta proof instead of the proof using sequence, instead, let's use a proof that uses sequence. Do you remember this sequential reformulation of the limit? So the limit as x approaches p of f of x. This is true if and only if what happens. Right. Let's pull it up. So one expects that it's probably in the stuff about limits and continuity in terms of sequences. You guys remember that note packet from like eons ago? Let's just pull that up. I feel like it was this one, translation to the setting of sequences. And here's the theorem that I'm referring to as sequential continuity. That U be a subset of R. Okay, here. That U be a subset of R. And F be a function. Oh no, not sequential continuity. I want sequential limits. The one below it. 3.2.3. Let's let U be a subset of R, and F be a function on U. Let P be a limit point of U, and L be a number in R. Then the limit as x goes to P of f of x is equal to L. I guess in our situation that L will be Y. If and only if, for every sequence of elements of the domain that is different from P, which converges to P, it follows that f of x of n converges to L. So instead of proving that the limit as x approaches P of f of x is Y, I'll prove that for every sequence x sub n
of elements of, no, I'm going to use wn because xn kind of already has a job. For every sequence, wn of elements of u different from p, such that wn converges to p, it holds that f of wn converges to y. There's what I'm going to try to show.
So, let's just read this out. So this is what I'm going to try to show. I need to show something in proof of every sequence of elements of u minus p such that wn converges to p. So I thought I'd start by considering any sequence of elements of u minus p such that wn converges to p. Let's do that.
Let's consider any sequence wn of elements of u different from p, such that wn converges to p. I need to show that f of wn converges to y.
So let's kind of draw a picture of that will give us some intuition about how this is supposed to go. So let's see. Here's some domain U. I have this uniformly continuous function f from u to r. What I've shown so far is there's this sequence of inputs converging to p such that f of x of n converges to y. So now we'll consider any other sequence wn, which also converges to p. Let's see. This will just be a cartoon of how the proof will go. The sequence wn, which converges to p, will f of wn converge? Yeah, because it will be Cauchy, so the exact same argument we used. So f of wn will converge. I would like it to converge to y. So let's imagine it didn't converge to y. Then here's what we'll do. I see like a sequence you could get by just alternating between blues and yellows, right? Would that sequence converge to p? It sure looks like it. Maybe we need an argument, but it sure looks like it. Then we would have a sequence up here that alternates between blue and yellow. Does that sequence converge? It'll have to, right? But in this picture, does it? So this picture must be wrong, so I think we can get a contradiction. Does that seem to be a reasonable plan of attack? So the big step was, let's take the sequence that alternates between blues and yellows. So let's let Zn be the sequence that alternates between blue and yellow. Let's let Zn be given by, well, W1 followed by X1 followed by W2 followed by X2 followed by W3 followed by X3. Or if you really like formulas for your sequences, let's take it to be X sub n divided by 2 when n happens to be even, and W sub n plus 1 divided by 2. Parentheses matter. I don't want n plus a half, I want n plus 1 all equal to 2. When n happens to be odd. And so let's just convince ourselves of this. Is that actually going to alternate between W's and Z's? So when you plug in 1 is left, so we get W sub 1 plus 1 over 2, that's W1. Next we'll plug in 2 is even, so we get X sub 2 over 2, that's X1. Then I get W2, then X2, yeah, that's the job. And let's see, just by looking at this picture, we were convinced that this sequence should converge to P. Do people want to see an epsilon n proof of that? Is there anyone for yes? Let's see an epsilon n proof. Okay, good. So let's see. That sequence Zn converges to P. So is that sequence Cauchy? So is f of Zn Cauchy? So f of Zn converges. I want the limit to be equal to y, or now let's call the limit L just to give it a name. So let's go back to the picture. If this sequence f of Zn converges to L, well then the yellow dots are like a subsequence of f of Zn, right? But the yellow dots already converge to y. So how does the limit of a big sequence compare with the limit of a subsequence? They're the same, right? If a big sequence converges, then so does every subsequence. So let's start with that. F of xn is a subsequence of f of zn. And let's just see. F of xn is like the even terms. So I think that f of xn is the same as f of z sub 2 times n. You guys see that? But it's a subsequence. So that means y, which is by design the limit of f of x sub n, by this observation that's the same as the limit of f of z sub 2n, but that's a subsequence of f of zn, which is L. So what can you conclude? Where does f of zn converge? On the other hand, the sequence that we're actually interested in, Wn, is also a subsequence of this thing. F of Wn, and let's see, you can check this if you want, is the same thing as f of z sub 2n minus 1. Give that a quick sanity check. Is that actually true? Or am I off by 1? If you plug in 2n minus 1 instead of n up there, you get w sub n back? Okay, that's it. So this is a subsequence of f of zn, so that means the limit of the little sequence is the same as the limit of the big sequence, but what's the limit of f of zn? Why? Okay, so let's just summarize, because this was a lot. I have now shown that for absolutely every sequence W of elements of U different from P, which satisfy that W sub n converges to P, we've proven that f of W sub n converges to Y. Well, remember, this sequential reformulation of limits is an if and only. There was an actual honest-to-God reformulation. It wasn't just a theory that one way. So I can now conclude that the limit as x converges to P of f of x is equal to that. In particular, that limit exists. How do people feel about that proof? It was a lot, and there was some cleverness in the design. All right, so step one was, well, shoot, how am I going to prove that something exists? First, let's try to get a candidate. And to get the candidate, I use this sequence. Hopefully, at least that part seemed sane and reasonable. And then once I had a candidate, well, pick your favorite way of proving that a limit statement is actually true. I like to call it sequential because I already had some sequences in there. One could alternately have done an epsilon delta. How many people would like to see that? Okay.
let's try to do it. So let's try to, I'll start in this space. So let's list all of the things that I'll use in this setup. So I'll use that this function f from u to r is uniformly continuous. And I will use that there exists a sequence xn of elements of u different from p, such that xn converges to p and f of xn converges to y. So those are the assumptions that I'll use. I'll try to now show the limit as x approaches p of f of x is equal to y.
And I'll try to make an honest-to-God epsilon delta pool of that green claim. How should an epsilon delta pool start?
Consider any epsilon bigger than 0.
Next, I have to come up with a choice of delta. And let's see, I do have one thing that gives me a choice of delta, right? I have the fact that f is uniformly continuous.
As f is uniformly continuous, there exists a delta bigger than 0 such that for all x and, well, there I called it p. P already has a job. For all x and y in u, if absolute value of x minus y is less than delta, then absolute value of f of x minus f of y is less than epsilon. And I'm going to put that epsilon in red because I could put any positive number there. So I'm going to keep it in red because maybe I'll need to do like an epsilon over 2 or something like that. So that gives me a choice of delta, at least maybe a starting choice of delta.
And let's see, this xn converges to b. So here's how what my plan is going to be. The sequence xn converging to b. And I'm going to try to look in a small neighborhood. And I'm going to try to take any element x in that small neighborhood. Let's see, these xn's are getting really close to p, right? And the f of xn's are also getting really close to epsilon. So eventually I can get these f of xn's to be really close to y. But this x I can also take to be really, really close to p. So that means I should be able to get this x to be pretty close to some of those xn's. Let's measure out how close, just so we can get a sense for how close these things are going to need to be. Let's draw one of these diagrams. Let's see. So I can get that to be a small set. I want to assume that x is close to p. I would like to get f of x to be really close to y. And, well, it seems like I should be able to get f of x to be close to some of those f of x events. also get them to be reasonably close to f of x. So that'll give me like 2 times epsilon there. So what do you think I want to divide u by? 2? See what I need to do to get that. So in order to get f of x to be really close to f of x of n, it would suffice to get x really close to x of n? That's true, right? So I want to get that. But these xn's, what do they get close to? P, right? They converge to P. So I should be able to get this to be really small. Oh, but that doesn't line up, right? This is now 2 delta. So what do you think I need to do? Divide by 2 again? Okay, so here it seems to be the plan of attack. I've come up with my choice of delta. Let's consider any x in u such that the absolute value of x minus p is less than delta over 2. That delta over 2 is positive, right?
So let's consider any x in u, and let's assume that absolute value of x minus p is less than delta over 2.
So let's see, the next things that I needed were xn to be within a delta over 2 of p. Can I get xn to be within a delta over 2 of p? Say by taking little n to be bigger than some big n? So let's write that down.
Since xn converges to p, there exists some choice of big N, and maybe I know there will be a second choice of big N from this. Are we happy now so far? So far everything is followed from previous assumptions? And let's see, I also seem to need f of x of n to be really close to y. But it is, right? F of x of n converges to y. Since f of x of n converges to y, there exists some big N too, such that for all little n bigger than big N2, absolute value of f of x of n minus y is less than epsilon over 2. And let's see, we also noticed that we needed these to be within epsilon over 2. So I think that's this red one. So now let's combine all this together. So well, I have 2 different choices of big N. So let's let little n be bigger than big max between big N1 and big N2. And let's compute some things. Let's start with the distance from x to xn, because we needed that to make this triangle walk. So the absolute value of x minus xn, and this picture even tells us what we need to do. I want to measure the distance x to xn. Let's do it by first measuring the distance to p from x, and then the distance from p to xn. Distance from x to p is less than delta over 2. Distance from p to xn is less than delta over 2, so this whole thing is less than delta over 2. Wait, but what's the whole, why did we do that?
We did that because now we know that the difference between x minus xn is less than delta.
So, distance from x to xn is less than delta. So the distance from f of x to f of xn must be less than epsilon over 2. Thus, the distance from f of x to f of xn is less than epsilon over 2. I think I said delta.
But now you can do the same thing again. I want to now know the distance from f of x to y, and I can do exactly that.
Finally, the distance from f of x to y, that's less than or equal to the distance from f of x to f of xn plus the distance from f of xn to y.
Right, that's just the triangle inequality. I skipped a step where I added and subtracted the same thing. But well, are you happy with that?
Let's see, f of x minus f of xn. Do I have a line somewhere in here that tells me that that's small? Yeah, what is it less than? Epsilon over 2. I guess that's this line. That needs little n to be bigger than big N 2. But it is, right, because little n is bigger than the max between big N1 and big N2. F of xn minus f of... Oh no, that was this line. F of xn minus f of y is less than epsilon over 2. Do I have a line that says f of x minus f of xn is less than epsilon over 2? Yeah, that's this line that we just got. So that's less than Chris. Epsilon over 2 plus epsilon over 2, but that's epsilon.
And I've run out of space to write my concluding sentence, which honestly I'm surprised I could even fit that much in this space. You guys may not have. This will be posted on. Well, let's just see what we actually did. Did we start by considering any epsilon bigger than 0? And then I came up with a positive quantity and considered any two things in the domain. No, any one thing in the domain, which was within a positive quantity of p, whose delta over 2. That's okay, delta over 2 is also positive. Did I then conclude that the absolute value of f of x minus y is less than epsilon? So here's, maybe that's a more honest proof of this theorem, because it didn't use this fanciness of a sequential reformulation. How does it feel with that? That feels okay.
Now, one of the reasons I wanted to do that, right before the lecture that I was supposed to start today, which maybe I've eaten up most of my time, I need to figure out how to time out these later lectures better than I have. Let's talk about extension of domain of uniformly continuous functions. And maybe it's a lie that I'll actually make to this content. Maybe I'll make it some. So I have just given you that result that says that if a function is uniformly continuous and you evaluate that uniformly continuous at any limit point of the domain, that limit exists. You can evaluate limits of uniformly continuous functions at every limit point of their domain. Well, so let's suppose you have the following then. Yeah, let's draw a picture first of what this goal is. So let's suppose you have a uniformly continuous function on, say, the open interval from 1 to 3. You have a uniformly continuous function there. It's not defined at these endpoints. There's a picture of a uniformly continuous function. Now maybe, well, all right, so let's just look at that picture. Does it look like you
could come up with an extension of this function. There's like an obvious choice about what value that function wants to take at 1. It's what you would get by filling in that open solver with a solid solver. So,
and there's an obvious value for what it would want to be at 3.
just fill in that open solver with a solid solver. So the question is, when can you do that? When can you take a continuously defined function, look at absolutely every limit point of the domain of that function, and find a definition that that function just has to have at those endpoints while still being continuous? That's what this note packet is going to be all about. So let's maybe start with some examples when you can't do that.
Yeah. So this is kind of review stuff, and I'm not going to make it through all of this note, so I think I'm going to save that as a reminder for next time. So here's ultimately the definition that this note packet is going to introduce and use. So it's that U be a subset of D be a subset of R. It's that F from U to R and G from B to R be functions. There's no assumption about continuity. There will be soon. I said that G is an extension of F. Yes, F of X is the same as G of X, but I believe X in U. So let's just see what that says. So the domain of G is the set B, which is bigger than U. So an extension of a function is a new function that has a bigger domain, but which on the Lidlaw domain agrees with the function we started with. So that's exactly what happened in that cartoon picture on the top, right? I started with a function which had domain 1 to 3. And I came with a new function that had the domain closed interval from 1 to 3. And on that, on the small set, the open interval, it agreed with the function I started with. And it was still continuing. So here's the question I want to ask. When can I do that? Because you can always just extend a function, right? If I give you a function defined on the open interval from 0 to 1, I can come up with a new function by taking that function on the open interval from 0 to 1 and defining it everywhere else to be 0. Right? That would be a function. So that's a stupid question if you don't qualify. If you don't qualify. So let's let F from U for be a continuous function, and U be a subset of V be a subset of R. Build there exists a continuous function G from B to R which extends that. How many people are taking / have taken abstraction people like this? You guys have probably thought about extension of functions at this point, where maybe the function might continue with such a homomorphisms instead. You maybe asked about when you can extend a homomorphism to a bigger set. But that's not, homomorphism isn't a word that is mentioned in this class whatsoever. A lot of the operations turn out to be homomorphisms. You can understand limits as a homomorphism, right? They're additive. Okay, I'm getting off topic, and I'm running low on time. So I want to know, when does there exist a function which extends another function, still continuous? And let's see one example when this doesn't happen. There's a function. There's the function whose domain is all of the real numbers except for 0. And let's just see. Does that function look like it's continuous on the set of all the real numbers except for 0? I mean, it does, right? If you can't actually see what's happening at 0, then it's a composition of continuous functions, and so it's continuous. So this function is in fact continuous. But let's see. And it's only not defined as 0. That's the only place where it's not defined. Do you think you could come up with an extension of this function to the whole of the real numbers which was continuous? Do the left and right hand one is yeah, so your question is maybe a more elementary one. Let's think about this function. The sine with a g function.
Is there a continuous extension of that function onto the whole of the real line? How many people would want to say that? How many people would want to say that? Why would you want to say that?
Is it going to be negative 1 or not?
Yeah, you need to pick a value equal to be 0. And no matter what value of 0 you pick, you'll get a discontinuity of 0. Because if it were continuous at 0, the limit of that function as x approaches 0 would have to be whatever value you assign at 0. Now what is the limit of that function as x approaches 0? Undefined. So you can't have g of 0 equals does not exist. That's not a valid definition. And so this should not have a continuous extension. Let's go back up here. Let's think about cosine of pi over x. Let's try to figure out why that should not have a continuous extension. And it's going to be the same. Right? Does it look like this function actually has a limit as x approaches 0? Certainly looks like it doesn't. It looks like it's, right, so the sine of the g function is trying to get close to 1 and get close to negative 1. This, the so-called topologist sine law, looks like it wants to get close to all of the numbers between negative 1 and 1. And the limit only takes one value, not infinitely many values. So this function sure looks like it shouldn't be continuous.
Or maybe the topologist sine function should be the... You might call that the topologist sine function.
So let's try to prove that. Let's try to prove that this thing does not have a continuous extension. So let's let f of x, well, r minus singleton 0 where if given by f of x equals to cosine of pi over x. The negative sign has been, the equal sign has been excluded. Let's suppose for the sake of contradiction that this did have a continuous extension. Let's suppose that it did.
Let's see then. Let's see, if there is this continuous extension,
then it would follow that the limit as x approaches 0 of g of x would have to be g of 0. If it were continuous at 0, right?
in particular, that limit would have to exist.
But let's see why it doesn't. Let's see, let's take x of n to be 1 over n. Since this function is actually continuous at 0,
By assumption for the sake of contradiction, the limit as n goes to infinity of g of xn would have to be the same thing as g of 0.
in particular, that limit would have to exist. Let's try to think about what g of x of n is.
And let's maybe even do that off to the side. So let's see,
So this function g should be the same as the function f that we started with, as long as we don't plug in 0. Is this sequence x of n ever 0? No, it's 1 over n. It gets close to 0, but it's never equal to 0.
So this function g of x must be the same thing as the cosine of 1 over, no, pi over xn. But xn is 1 over n. So this will be the same thing as the cosine of n times pi.
And let's just go over, what's the cosine of n times pi? What's the cosine of 0 times pi? Cosine of 0 is... what's the cosine of pi? -1. So when n equals 2, we get -1. What's the cosine of 2 times pi? 1 again, so it's back up to 1. What's the cosine of 3 times pi? So there's like a problem here, right? It looks like g of xn is alternating between +1 and -1. So that sequence converge. Alternates.
So this function g of xn is divergent.
by a reason which I won't explain to you because you guys have just explained it to me. If you like, that outline is, here are two subsequences which converge to different things. I've got a subsequence which is always one, and a subsequence which is always negative one. So the sequence is divergent, but the sequence is convergent. So we get a contribution.
So it must be that the assumption that we made at the beginning of this proof is false, namely the assumption that there exists a continuous extension, must not be true. And so we see that this function does not have a continuous extension. Now the thing that stopped us from doing this was the fact that the limit as x goes to 0 of g of x did not exist. So maybe if we start with a function where the limits always exist, we can always come up with a continuous extension. What do you think? Does that sound believable? Oh, that's the content of this note packet. That's what it is. As a reminder, no class Monday, math this week instead. Also as a reminder, how many people are planning on signing up for the math this week competition? Okay, that's more than last time. I'll remind you that there will be extra credit associated to it. Does that increase the count of people who want to? Okay. Is it because the rest of you just can't make that hour? Okay. I should stop the recording before I turn off the projector, otherwise